We are going to finish up with another of our short developer updates. This one is going to come from Richard Mills, who's coming to us from Portland for this meeting. So Richard has the honor of having made the only top-level object addition to PETSc since the Tau merger, so probably within the last 10 years or so. In a merge request that he got, that we got the push in and we got it in before the meeting, so really happy about that. So we'll let Richard tell us more about it.
How long should I talk, Toby? We're already supposed to be on the break.
No, you can have 15 minutes because I misplaced the poster boards, so we will have to. We have to have posters tomorrow at lunch.
Okay, let's see.
Clip it.
Maybe like.
Fine.
Let's see. How's that?
That's great.
Okay. All right. Okay. Let's see. And it's okay. Let me set a timer so I don't talk too long. Okay. Okay, I won't keep us too long from our afternoon coffee break, but thanks. I'm Richard Mills from Argonne National Laboratory West in Portland, Oregon, my house. And I'm going to talk today about a brand new sort of project I've been working on in PETSc with help from a couple other people on and off for a number of years, and it's finally made it into PETSc main. So I'm going to talk about PetscRegressor. It's a new top-level component for doing regression and actually classification problems and viewing them all. They're kind of one and the same, you know, logistic regression as a classifier, stuff like that. It doesn't actually, it's really new. It hardly does anything right now. It does linear regression with some optional regularizations. But it provides like this basic infrastructure and a general API for doing machine learning tasks at a sort of higher level of abstraction than the purely algebraic, you know, PETSc solvers view. And it's the first component of what I hope can get grown into a sort of machine learning toolkit in PETSc that will, you know, implement the machine learning algorithms that can really benefit from using fast, parallel, robust solvers in PETSc. And this part, I think, is also really important to be seamlessly usable with existing machine learning workflows, which are just overwhelmingly implemented using Python tools. So we need kind of first-class Python support. So let me first address the question, like, why am I bothering to do this? Because I've been doing distributed memory parallel programming for a long time, and it is actually a huge pain. You know, so why would I want to do this? Well, so when I'm not building simulation codes, I've also worked a lot on kind of data mining and machine learning tasks with very large geospatial data sets, with like climate scientists and ecologist colleagues for a number of years. And I actually got into this when I found out some of my ecologist colleagues at Oak Ridge National Laboratory were trying to do things like run a principal components analysis on this big data set that wouldn't fit in the memory on their workstation. So they would actually just let it run literally for a month. Because it would just have to be, you know, swapping in and out of the disk, and oh gosh, if the power went off, you know, halfway through, they didn't have checkpointing, they had to start over again. I was like, man, guys, you know, this is just linear algebra, and I know how to do this in parallel. So I wrote a one-off standalone code for doing that, you know, I've done this in a few cases, the reason I've had to do it is because, you know, existing tools for a lot of these kinds of data analysis just aren't really designed to scale to big data sets. You know, the tools that do offer parallelism usually only provide a shared memory, you know, OpenMP kind of parallelism. There are some tools that do distributed memory parallelism, but it's usually a data parallel thing, so your model gets replicated across many nodes. Training samples are assigned to nodes. Training occurs using a local batch. And you know, if you have a big model, then this doesn't work very well. And The other thing is these batch size limitations can actually be pretty problematic, because you need a large enough batch size to match the number of parallel devices you're trying to keep available, and really large models still can't be trained with this approach. And I like this figure that I think Jed Brown first introduced it to me from this 2021 paper on this ML-Perf HPC benchmark, where they were running a deep learning benchmark on a bunch of the big computers at the time. Like Fugaku needs a really gigantic batch size, and what happens is this really increases the number of epochs required to get your model trained. It's good to not have to always be trying to fit things into this batch or mini batch way of doing things. Okay, so I mentioned I've written some standalone codes over the years. Going forward, I want to do this using PETSc. Why do it using PETSc? Of course, PETSc's got a long-standing emphasis on parallel performance and portability. Independent from specific vendors as much as possible, and compiler tool change, and importantly, several available GPU backends now that are working pretty well. It's got a lot of support for extremely flexible data decomposition and data management. Supports sparse data structures and actually data structure agnostic interfaces. It's got a lot of really cool advanced optimization methods that I don't really understand because I'm not an optimization guy. And it provides high-level adjoint, algorithmic differentiation in TS adjoint, which potentially opens up many approaches requiring differentiable programming. And of course, many of the simulation codes that are being used right now to generate data sets that physics-based machine learning things are trained on already use PETSc. So why not try to put some support for this into PETSc itself? Okay, so I thought I'd actually just here's basically what it looks like. You have in this example, X is a PETSc matrix of training data where each observation is packed into a row. Y is the PETSc vector that's a target training vector. I center the target vector here, create a regressor that looks just like, creating a SNES object or tau object or whatever. You can control a bunch of things from the command lines. You could put things on GPU if you want, using the right, GPU linear algebra types. And then we just fit the model and make a prediction with it. And we use a fit and predict paradigm that comes from scikit-learn, very popular classical machine learning framework. And then you can get the model parameters and prediction out of that. And then we also have a Python API that looks kind of the same, but Pythonic. I wanted to say a little bit. I don't want to spend too much time in there because you can go look in PETSc main. At the implementation. So I wanted to look in the linear.c implementation to just kind of show, what is this automating us and saving us? Because, there's actually some nice examples in PETSc and in tau in this least squares directory of tutorials where they're doing compressive sensing. So they're doing least squares regression problems, but there's a lot of setup that has to happen, and I'm trying to pack all that setup that you would otherwise do all the time manually into these things that live inside PetscRegressor. Show an example of setting up the linear case. One, if we're fitting the intercept, we do a bunch of stuff. So we actually, I don't fit the intercept unless you ask for it, and it's done separately from fitting the rest of the model, and that is because you don't want to be regularizing your intercept fit. That's a bad idea, so that's why I do it separately. So I do some things here to make it not a pain, and in fact, I also actually, I created this mat centering type that basically lets you get a centered data matrix without messing up the sparsity of your problem if you're working with sparse data. That's what the setup looks like for that. And then you can solve things with a KSP in some cases where you're not trying to do regularization. You can solve things via tau. And we're just doing this setup here. And, I think Toby mentioned, tau right now works all on these callbacks. So we're setting up this residual routine, Jacobian routine. I'll show them the next slide. And then in this case, I'm actually just hard coding the use of the bounded regularized Gauss-Newton, which has its own its own ways of specifying the regularization terms. And once tau term is in there, I'm going to be able to add a lot of other cool things. Like right now, I'd like to do. I support lasso and ridge regression. There's also a thing called elastic net, which is a combination of these. It'd be super easy to do once tau term's in there. It's just another thing to add. And then, I'm doing the callback function, so valuing the residual is just, this least squares thing, and then actually, in this case, the Jacobian doesn't do anything, so that's that. And then, when it fits the model, let's see, I call KSP solve or tau solve as appropriate once we've done all that setup. And then, I just wanted to emphasize here, calculating the intercept is done totally separately so you don't get this mixed up in your regularization. Okay, so now for an actual demonstration, we're going to open a Jupyter notebook, and this is actually the first time I've ever made a Jupyter notebook. I've run a bunch, but I've never actually made one, so hopefully it works. All right, so, okay, is that big enough for people to see? Okay. Let's see, so I will go over here and tell it, let's restart and clear the output. Okay, so I wanted to do a sort of non-trivial problem with scikit-learn and then show how you can just drop PetscRegressor right into there. And so what I did was I started from this scikit-learn example that is a compressed sensing tomography reconstruction example. And I've actually, so here this is pasted in from the example that comes from this URL right here. So it just does some NumPy and SciPy stuff to set up the problem. So I'll go ahead and let that run. All right, so let's see, I'll tell you what it's actually doing. So the above code is generating this random material field that we want to reconstruct, and then it simulates a computed tomography scan. So you're making single pixel images that are constructed by computing intensities along linear projections through this material from different starting points and angles. And of course, you only want to take a few of these because maybe it's really expensive for your geophysical survey you're doing, or X-ray imaging. You don't want to give people too many rads. So you want to be able to reconstruct the original material from a sparse set of images, so it's a compressed sensing problem. And I put some code in here to actually illustrate what this is actually doing. I show two different slices, and so here's one slice, and these are the intersections, and then another slice going through here. Here are these intersections, and basically you get the intensity that your sensor measures, but basically just like adding up the number of pixels that are intersected. So let's see, and I'll actually go ahead and plot. This is what the entire collection of CT intensities looks like. Okay, so this reconstruction problem can be formed by solving with an approximate regularization, this least squares problem, this form, where X is this projection operator, which is highly underdetermined, built above for the different rays. Y is the vector of measured intensities, and W is the thing that we want to recover. It's the vector, describing the material being imaged. So let's go ahead and actually plot. That's what the projection operator is, making a bunch of different, slices through the thing. And okay, and then let's see. So I've taken the. So this is the W, the thing we want to recover. So you take this image and you unroll it into a vector. CT data, you unroll it into our target vector here. So now we're set up to solve a regression problem. So in this example from scikit-learn, they do it two ways. They try ridge regression, which uses an L2 penalization, minimizing this, and they also do L1. So both of these you're trying to make your coefficients somehow small. But ridge regression, because it's using L2, kind of makes it kind of minimizes all of these things, whereas L1 is going to do this in a sparse way. So okay, so I'm just running running these separately so I can time them. The L2, the ridge fit is really quick. It's very easy to do. It's a lot harder to do the L1 because of that non-smoothness in there. So it actually takes quite a while. And I looked at what scikit-learn's doing. It's doing like coordinate descent. It's terrible. But so it took like 9 seconds about. Yeah, okay. So yeah, it's like from 1960s. It's really old, so I think we've got better things in PETSc. Okay, so ran both of those. Let's plot the reconstruction. And so you see here, here's our original image we want to recover. You can see outlines of the structures we're trying to get in the ridge regression fit, but there's a ton of artifacts in here, right? You can see all the lines for the different scan directions. You get this weird kind of circular, you're looking at this weird annulus thing, but in the L1 penalization, you recover it perfectly. So pretty cool. That's L1 doing what it's supposed to. Okay, so now I want to demonstrate that I can just take this existing scikit-learn workflow and use the PetscRegressor, PetscRegressor for Pi bindings. So I'll go ahead and run this. You do the initial, PetscRegressor object initialization and setup, just like you would if you're doing a tau object or a SNES object or whatever. Just doing some indexing here, and then I got to put our x and y into PetscMat and vec objects. So I've done that. And now I will do the actual regressor fit, which, let's see. Okay, yeah, I'm doing the L1. Yeah, so I told it to do the tau monitor, so we see, okay, it takes like 39 steps. And the thing ran in 1.8 seconds instead of like 9 seconds. So that's good. And let's see, now let's extract the data we want to plot. So we actually, do this get linear coefficients returns a PetscVec. And so I'm going to take that and then, get the array out. And then let's see what, let's see what actually happened during the solve. So we have a view method like all the PETSc objects do. And so you see I'm doing a linear regressor, and that subtype of linear regressor is lasso. I see the computed intercept. Under the hood, we're using tau BRGN, and et cetera, all the details you want of the solvers. So now let's do the same thing with a ridge regressor for comparison. And this will run really fast. Yeah, it takes like 2 Newton iterations. Okay, so, and then again, we can look and see what PETSc solvers were used under the hood. Instead of looking at the viewing the PETSc regressor itself, I'm going to show you can grab the tau object out of that, and then you can manipulate that however you want. In this case, you just want to view it, and we see the same kind of information. BRGN with the L2 pure regularization, and converge real fast. Okay, so now let's actually plot the PETSc solutions along with the scikit-learn ones to see how we did. And looks basically identical. So it did work. And it was actually really easy to just put this into an existing scikit-learn workflow. All right, so I should finish up. I'm actually going over time. Okay, so what are the future plans for this in my vision? One is that I'd like to add a bunch of additional regressor or classifier PetscRegressor types. Toby has mentioned interest in generalized linear models. I'd certainly like to do logistic regression. I would like to interface to the Permon SVM machine that the guys at TU Ostrava have done, or VSB Ostrava. This is a very nice support vector machine implementation that uses PETSc. We can just wrap it. K-nearest neighbors, I think Gaussian processes actually could use a lot of the things that PETSc does in sparse land, or insert your favorite regressor classifier here. This is really sort of a call to, like, if anybody's doing stuff like this, it'd be great, to work with you and get more things into PETSc. I'd also like to add several other top-level machine learning components. Originally I was interested in doing clustering stuff. Like Srinivas at Argonne's working on non-negative matrix factorization with Hansel. We want to support just general dimension reduction kind of things. And then, less glamorous but equally important, there's a lot of just helper or utility routines that we need, like, really ways to do things like easily do cross-validation with PETSc data sets that are stored in PETSc parallel objects, and more routines to make it easier to get data back and forth between scikit-learn, PyTorch, et cetera, and PETSc. And the kind of vision for the future is, I'd like to be able to have PETSc providing easy options to speed up the expensive portions of existing machine learning workflows using PETSc solvers. And then what I'd really love to be able to do is support doing machine learning like in situ with your big simulation. because the way people usually do it now is they have a big simulation, they submit it to the batch the batch scheduler on a big machine, they wait a couple days, it runs, then they have to suck that data down to somewhere else and mess with it before maybe running another simulation. It'd be great if you could just kind of do some of these things, just at the end of your job or during your job. I think that'd be great. And then in fact, that would facilitate like online approaches to training ML models from simulation data, where you could kind of have your machine learning workflow is being constrained by the physics as you are running, your physics-based model. So that's it. Okay. So thanks. So check it out, and I'll post like this. I'll be sticking this Jupyter notebook like into the repo and the demos and stuff once I get my MR accepted. That actually I was missing a couple PETSc for Python bindings to make this work that I discovered while doing the Jupyter notebook. So thanks, and discussion. Just running to go get your coffee or whatever. Thanks.
It's really exciting to see that we're making some progress along these lines. Well, so Matt, do you want to say anything about what's going on?
I will in a second. So what is your attitude toward random forest in here? Is it something that you would think to go in for classification?
I mean, if it makes sense to have a parallel implementation of it in PETSc, sure. I've never implemented random forest. I've just called it from little things. It's certainly. I honestly, I believe that a whole lot of things that people use an expensive, deep neural network for can actually just be solved with like a boosted random forest.
That's what I think too. That's why I thought we should put it in so we can test it.
Yeah.
So, okay. As I said,